Hello everyone, I'm very happy to be with you virtually today. My name is Chen, a PhD student from Pennsylvania State University. You can call me Louis. In this talk, I'd like to share with you some outcomes of my recent research work with my lab mate Zheng Peng and my advisor Xinyu. This talk is about an exploitation approach which can bypass many protections in OS kernel. Many black hat talks will describe how to find new vulnerabilities or new exploitation tricks. However, in this presentation, I'm going to review an exploitation approach that has existed for almost a decade. We demonstrate that this attack is not only severe, but also general. Thus, we propose our mitigation design to deal with this attack. This presentation is organized as follows. First, I will introduce several kernel protections that we're going to bypass, as well as some kernel-sensitive data we want to leak. Second, I will describe the exploitation approach using two examples. One for Linux kernel and another is for Windows kernel. Followed by this, I will show how we track down elastic objects in the kernel codebase. Elastic objects is the key in this attack. I will display the severity of this exploitation approach and the reason why we need to study the generality of this attack. After this, I will describe the way we use to study the generality and the outcome of the study. Finally, I will go through several kernel mitigations that seem to be able to circumvent the attack, but they fail in the real world. Therefore, we propose a mitigation which is simple but effective. This presentation takes about 40 minutes for 30 pages. If you have any questions, feel free to ask. And also, I paste my contact at the last page of the slide, in case you don't have a chance to ask questions. I hope you can enjoy the presentation and send me your comments so that we can further advance our research. First things first, I will describe several kernel protections that we plan to bypass. The first protection is stack canary, which is pretty standard protection in Linux, FreeBSD XNU, and Windows kernel. The idea is quite simple. When having a stack buffer overflow, the adversary can overwrite the return address in current stack frame. Later, when the function returns, the kernel execution is directed to the malicious address. To protect this overwrite, during the prologue, the kernel places the stack canary, which is several bytes of random value, right below the return address and old EBP. During the epilogue, the kernel tests the canary on stack against the stored one to see if any corruptions happened. If stack buffer overflow is triggered, the stack canary is tempered. Thus, when the kernel finds a mismatch between the canary on stack and the stored one, this means stack corruption has happened, and the return address is no longer trustworthy. To bypass this mitigation, the adversary either uses brute force method or relies on information leaking. The brute force method is to guess the canary byte by byte, which reduces the complexity from 64 over 2 to 8 over 2 on a big O. Information leaking is another approach in which the adversary can leak the canary to user space. In this presentation, I will show how we can obtain a leaking primitive from a limited write primitive to expose the stack canary. There are many other protections of the similar goal, for example, the ARM pack and the K-stack overflow from GR security. As they rely on specific hardware features or are not adopted by the mainline kernel, we don't elaborate on them in this presentation. The second protection on stack I want to introduce is config initial stack all and config GCC plugin stack leak. Both mitigations are responsible for poisoning the kernel stack at the end of system call. The kernel is buggy, as we all know. One type of the bug is uninitialized stack. The adversary can exploit this type of bug using stack spray. When the machine enters the kernel mode, the kernel stack is used to store local variables. Some of the local variables can be sensitive, for example, keys for encryption. The adversary can use a system call to store these sensitive data on kernel stack. and then he or she can use another system call to trigger the uninitialized stack bug. As part of the stack is uninitialized, the sensitive data is not erased from the stack. Later on, when part of the stack is copied to user space, the sensitive data is leaked. Last year, a stack-based information leaking in A2MP of Bluetooth is discovered, basically practicing this idea. To circumvent this leaking, there have been proposed many protections. For example, randomize the base address of kernel stack so that the two system calls are not using the same memory region. The two protections I mentioned up here follow another approach, which is to poison the kernel stack at the end of system call. Since the sensitive data is erased, the adversary cannot use the uninitialized stack bug in the second system call to leak data. The difference between the two mitigations are that the former is implemented in GCC plugin and the latter is in kernel code base. And also, the former poisons the whole stack and the latter only erases the stack region that has been used in this system call. No matter which mitigation is used, both have the limitation that it only works for multi-system call stack attack, because poisoning happens at the end of system call. If the adversary can read the data before returning back to user space, information leaking is still doable. In the exploitation approach I'm going to describe in this presentation, a limited write primitive on kernel heap can be used to leak the data on stack in one system call that not using an uninitialized stack bug. On slab allocator, one of the protections is config slab freelist hardened. This protection includes 3 patches, and I show the diagram of one patch on the slide. The freed slots in slab allocator are chained using a singly linked list. The head of the list is named freelist. When a slot is in free status, the first 8 bytes are used to store the address of the next slot in the list. This is the situation before the patch is applied. After the patch is applied, the first 8 bytes of the freed slot stores XOR result of first the address of the next slot, which is free slot 3 in the diagram, second, address of the free list head, and third, the random number. Without the patch, the adversary can forge a fake address using heap buffer overflow and mislead the kernel to return the memory region indicated by the fake address in the next allocation. This allows the adversary to tamper the data stored in the fake address. However, with this patch, the kernel will calculate the address of the next freed slot by reversing XOR's data in the first 8 bytes. Even if the adversary can forge the data using heap buffer overflow, the calculated address is not what the address wants. This is because the random number is involved in the calculation. According to one study early last year, the entropy of the hardening is very low, and thus forging an address is possible. As complement in the exploitation approach I will describe in this presentation, the first 8 bytes after XOR can be leaked with the limited write primitive on kernel heap. The leaked 8 bytes can then be used for forging. I call the 8 bytes as heap cookie in the following slides. Due to this weakness, the kernel has further hardened the heap cookie design after version 5.6.4. Similar idea is also adopted in XNU using a different implementation. Another protection on slab is a pair of initial on-alloc and initial on-free. These two mitigations share some similarities with the stack poisoning we've discussed in the previous slides. Like kernel stack, the heap object encloses sensitive data like function pointer and keys for encryption. Without the protection, the content in the heap object is left unchanged after the object is freed. Later, when the slot holding the object is recycled for the following allocations, the adversary can use an uninitialized heap bug to leak the data. To this end, the two mitigations are responsible for zeroing out the heap object at the time of freeing and reallocation, respectively. As such, the sensitive data is removed and leaked data is all zeroed out. The two protections work for use-after-free exploitation and double-free exploitation because the two types of vulnerability need to reason about freeing and reallocation. However, when the heap object is in use, the sensitive data is stored on the kernel heap. This gave us the chance to leak the sensitive data in the heap object using the leak primitive obtained from a limited write primitive. I will elaborate on this later. The next protection I want to describe is KASLR, kernel address space layout randomization. On the slide, I show part of the kernel memory layout. With this protection, the loaded kernel text image could be anywhere from A to 0 to C to 0 as long as it complies with the alignment policy. The loaded kernel modules could be anywhere from C to 0 to C to 0 to 4 to 0 as long as it complies with alignment policy 2. This is the situation of x64, and other architectures are similar. KASLR is adopted in XNU and Windows. This protection works because it's very hard for those exploitation approaches to reliably jump to the target code if they want to execute kernel instructions for malicious goal. To defeat this protection, the commonly used approach is to leak the address of a global variable or function point or function. Then the adversary can calculate the base address of loaded kernel image or module through offset. That's why I say in the previous slides, the return address and the function pointer are sensitive data because they store the address of functions. Once their value is leaked, KASLR can be bypassed. This is the first shortcoming of KASLR. Another shortcoming is the low entropy because there are only so many locations a kernel can fit in. Someone thinks a attacker can guess the base address without too much trouble. As such, KASLR in function granularity is proposed. I cannot go into details of this new protection because it's still in development. The main idea is to randomize the address of functions when loading the kernel image. The entropy is much higher in this granularity, and one leaking is far away from being enough to defeat this fine granularity protection. Apart from protections which rely on hiding sensitive data, on this page I list two types of sensitive data that can be leaked from kernel according to Andrew's exploit. The first is the content of the file etc shadow in the keyring demo. This file stores the hashed value of the user's passwords. The adversary can use hash collision to reverse engineer the hashed value and obtain the password. The owner of this file is root and the group is shadow. With the leak primitive, the adversary can scan the physical memory to search for the pattern because the first entry of the file is always for root and loaded to the beginning of the page. The second is interrupt descriptor table. When interrupt happens, the kernel will jump to the interrupt procedure for further process. The offset to the procedure entry is stored in the table. If the adversary can leak the offset, he or she can calculate the base address of loaded kernel image and thus bypass KASLR. There are many other types of sensitive data in kernel. Due to the time limit, I cannot enumerate them, and I'm happy to learn more if you know more about them. The exploitation approach I want to describe today is not a new attack. It is used in Pontoon 2017 for CVE 2017-7184. In the exploitation of this vulnerability, the attacker uses a flexible structure named Transform Replace State ESN. As shown in the diagram on the slide, this structure has two fields. One field is bitmap length, which is an integer, and another is bitmap, which is a buffer. The length of a bitmap is determined dynamically and indicated by bitmap length. When kernel uses the structure, it obtains the length of bitmap from bitmap length. To do the exploitation, the attacker performs heap function and places transform replace state ESN right after the vulnerable object. Then the attacker triggers heap buffer overflow to overwrite bitmap length. The bitmap length is enlarged and misleads the kernel to believe the size of bitmap is larger than actual size. Later, when receive message system call comes, the content in the bitmap is copied to the user space via netlink put function. Since the bitmap length is enlarged, the heap region after the bitmap is also copied out, causing an overread. The attacker places a file structure after the bitmap. The file structure has a function pointer field named FOP, which points to a static variable ext4 file operations. By leaking the value of the function pointer, the attacker knows the address of a static variable and then calculates the base address of loaded kernel image for bypassing KSLR. The flexible object has two advantages in exploitation. One is its ability to leak data, another is the size of the object can be determined dynamically. So it can be allocated to several general caches to be paired with vulnerable object and victim object. The same attack is observed in Windows kernel exploitation. The example on the slide is the one from a previous Black Hat issue talk by Yu Wang. In this exploitation, the attacker uses the useAfterFree tag prob list to override C entries and ifirst free fields in the zombie tag prob list. Tag prob list happens to be an elastic structure, similar to the one in the previous slide. C entries, the length field, and ifirst free is the flexible buffer. After corrupting the C entries and ifirst free fields, the attacker continues to rewrite tag WND object to obtain arbitrary read and write. From this example, we know that elastic object attack is not specific to Linux but also other OS kernels because the implementation of elastic objects follows similar patterns. Before we describe what else we can do using elastic objects, we investigate its implementation patterns. On the slide, I display three other ways of implementing elastic objects. The first way is to have a large buffer defined in the middle of a data object. The length field within that object indicates the actual buffer size, or more precisely speaking, the actual bytes used for storing data. At the time of defining the actual number of bytes used for storing data, kernel typically examines the length field and ensures it doesn't go beyond the boundary of the large buffer. However, we discover that the kernel doesn't always enforce this check at the time of reading data from that buffer. As such, it eases an attacker's ability to manipulate the length field and thus construct a buffer overread. In the second and third way, the two implementations do not enclose the length field and the flexible buffer in the same kernel object. Instead, they place the length field and the flexible buffer in two individual kernel objects. The difference is that the second implementation contains an explicit reference to the flexible buffer, while the third implementation references the flexible buffer through a third intermediate kernel object. Now, let's see what we can do using elastic objects. The assumption of this attack is that we've already obtained the write primitive on kernel heap. We use that write primitive to tempo the length field as well as the pointer field. Later, the value of length field is propagated to the size argument of copy-to-user function. Copy-to-user function has three arguments. The first argument is destination, indicating where the data is copied to. The second argument is source, which indicates where the data is copied from. The third argument is size, which represents how many bytes of data to copy. Now we've already controlled the size argument. On the right side of the slide, I show three situations where the source could come from. The first situation is the source argument is the address of kernel stack. In this situation, if we enlarge the size value using the write primitive, we can overread the kernel stack and leak the stack canary and return address to user space. The second situation is the source argument is the address of kernel heap. We can overread the kernel heap to disclose function pointer and heap cookie. The third situation is the source argument is from the pointer field in the elastic object, and it is also tempered by the adversary using the write primitive. In this situation, we can make the source argument to be any kernel address. As such, we can leak sensitive data like etc shadow or interrupt this crypto table, which we mentioned in the previous slides. The severity of this attack is obvious. If the adversary has a limited write primitive on kernel heap by triggering the vulnerabilities like slab out-of-bound write, use after free, and double free, he or she can transfer this write primitive to obtain a leak primitive. This capability enables the adversary to leak stack canary, return address, encrypted heap cookies, function pointer, etc shadow, interrupt this crypto table, and many other sensitive data. With this sensitive data in hand, it becomes easier for the attacker to perform following exploitation steps. Regarding the generality of this attack, it's unknown, unfortunately. First, we don't know what else channel functions in kernel, like copy to user, can provide us with the ability to communicate between kernel space and user space. Second, how many elastic structures and objects are there in the kernel codebase? If we only have 2 or 3, it's very hard to cover most slab caches, let alone to say pairing them with a vulnerability. The third question is, even if we have enough elastic structures, it doesn't mean the length field and the pointer field of them can be propagated to the channel functions. Without this guarantee, the adversary can hardly control the size argument as well as the source argument. The last question, giving a vulnerability, does it provide us with the right primitive to overwrite the length field and the pointer field? It's possible that most vulnerabilities don't have that strong capability. However, generality problem is of vital importance because it is related to the questions that do we need to pay attention to this attack and do we need to need a new mitigation? If the attack is very ad hoc, I don't see any necessity to build a new mitigation. Probably simple patching is enough. As such, our research work mainly focuses on studying the generality of this attack. We define generality from 2 perspectives. First, is there enough number of elastic objects in the kernel? And second, can most vulnerabilities provide us with the capability to make use of elastic object for exploitation? First things first, we identify some channel functions in the kernel and list them on the slide. We group them into 3 categories. The first one is memory access API, which is copy to user. The second one is specific to netlink socket, which is a networking between kernel space and user space. To use this functionality requires network administration capability, which can be granted in the user namespace. So you don't worry about you don't have the capability to use this socket for exploitation. Take the netlink put function as the example. Attribute length, which is highlighted with underline, is the size argument, and the data, which is in bold, is source argument. The third one is general networking. For example, skb put data, in which length is the size argument and the data is the source argument. Some channel functions are the combination of 2 functions. For example, in netlink, the return value of netlink message data is the source argument, which is later used in memory copy function. The size argument is count in memory copy. No matter what the function prototypes are, all of them have a source argument and a size argument. Our analysis begins from these channel functions. The first step in our static analysis is to identify the leaking anchor, which is invoking 2 channel functions in the codebase. I use red to represent source argument and green for a size argument in the channel function. The first step is to check where is the length from. In the diagram, the length is from a structural variable named uPayload. Its type is user key payload. The third step is to check where is the size from. In the diagram, the source is the return value of keymalloc. The type of the source is user key payload 2. We can clearly see that the source and the length are both from the same structural type. Besides, we can learn that this structural variable is on the heap because it is generated through allocation. What's more, user key payload is a standard flexible structure because its size is a constant plus a variable. The offset of the length field and the flexible buffer can also be tracked down. Through above analysis, we can learn which slab cache is responsible for holding the object, though the user key payload is exactly the elastic structure that we are searching for. The last step of the analysis is to collect the constraints along the path from the ankle retrieving length to ankle that leaks data. We do this examination because we want to see whether the kernel enforces the checking of length fields. If the kernel says, hey, the length cannot be too large, the leaking probably doesn't work. In the example on the slides, the kernel only ensures that a user-controlled parameter buffer length is larger than the data length. Therefore, this checking doesn't influence the data leaking. Finally, we obtain a record for each identified elastic structure. We know the structure name, the cache holding the object, the offset of length field, allocation sites, leaking sites, as well as what types of sensitive data can be leaked. In total, the static analysis tracks down 49 elastic structures in default configuration. We use kernel fuzzing and manual analysis confirmed 38 of them. We list these structures here. In the table, the first column represents which cache the object can reside in. The second column is the structure name. The third is the offset of length field and pointer field. The fourth is what sensitive data can be leaked. The fifth is the privilege required to operate the object. And the last column is the path constraints. To sum up, most general caches are covered by our identified structures. Note that the number 36 and 38 are for structures, not objects. If we count the number of objects and the program sites that use objects, the statistics can be thousands. From this perspective, the elastic objects are pervasive in kernel codebase. We used 31 vulnerabilities to examine what we can do using elastic objects. The results showed that 23 vulnerabilities is enabled with KSLR bypassing and heap cookies leaking. 12 of them can leak stack canary and 5 of them can perform arbitrary read. Thus, we want to draw a conclusion that elastic object attack is general in Linux kernel. How about other operating systems kernels? In XNU, the static analysis tracks down 16 structures in FreeBSD, and in FreeBSD we have 12 structures. We use in total 9 CVEs in FreeBSD and XNU. 5 of them can bypass KSLR. 4 of them leak heap cookies because FreeBSD doesn't have heap cookie. 3 of them can perform arbitrary read. It seems elastic object attack is an issue not only in Linux, but also in FreeBSD and XNU. Someone may ask that we can use elastic object for leaking because the kernel data can be copied from kernel space to user space via channel functions like copy to user. Is it possible that we use elastic object for arbitrary writing using functions that copy data from user space to kernel space? To answer this question, I add copy from user function to our static analysis and found 3 candidate structures. The first is IO vector, a commonly used one. However, this structure is enforced with length checking. The 2 others are DM-IO control and FD table. To overwrite requires data rates and the time windows is very small. It's impractical to use them for arbitrary writing. I want to emphasize that this study is limited because I don't include other functions. In fact, I know some exploits use elastic object to realize an arbitrary write. I plan to leave it as my future work. Since we've released our code, I also invite you to do some contribution if you are interested. There are several mitigations in Linux kernel that seems effective to prevent this elastic object attack. The first potential mitigation is free list randomization. Without this mitigation, the freed slots are chained in the list linearly. This means the freed slots are physically continuous. With this feature, the adversary can predict the slab layout and perform stable heap function. With this mitigation, the freed slots are shuffled when kernels create slab cache. Thus, the order of freed slots are randomized. In this way, the adversary cannot predict the slab layout, and it's harder for he or she to exploit slab outer-bound write vulnerability. The limitations of these mitigations are first, it has no effects on use after free, double-free exploitation. This is because the exploitation of these two types doesn't require to predict the slab layout. And second, there are many bypassing techniques against this mitigation. For example, heap groom, which is to first allocate a bunch of placeholder objects and victim object to the kernel heap. Then the adversary frees the placeholder objects and leaves holes on the heap. After this, he or she can allocate the vulnerable object to the host to perform heap function. Another technique to bypass the free list randomization is the free list reversal. Due to the time limit, I will not elaborate on them in this presentation, and more details can be found online. The second potential mitigation is config GCC plugin random structure. This mitigation tries to randomize the order of fields in the structure under the compilation phase. It prevents attackers from predicting the offset of sensitive data within the structure. Take the structure on the slide as an example. The attackers want to overwrite function pointer field initial to hijack control flow. Without the randomization, the offset of the initial field is fixed and predictable. With the randomization, the initial field is shuffled to another order. Thus, the override doesn't always work. As such, this mitigation seems a threat to the attacker. However, I want to say that this defense relies on a random seed to perform randomization, and the protection of this seed is not trivial. For example, Linux distros have to expose the random seed to their users for building third-party kernel modules. This is because the third-party kernel modules need to know how exactly the structure is defined after layout randomization for using them. The mitigation works well in house building kernel if the random seed can be protected appropriately, but for distros like Ubuntu and Debian, it's not very practical. The last potential mitigation is config hardened user copy, which is important from PAX user copy. This mitigation examines the size argument of copy to user. If the source argument is a kernel stack address, this defense ensures that the size argument is smaller than the frame size. Only data in the current stack frame can be copied out. If the source argument is kernel heap address, this defense ensures that the size argument is smaller than the slot size. A cross-site overread is disallowed. The similar mechanism is also used in XNU kernel. While this technique can mitigate the threat of some elastic objects, it suffers from two problems. On the one hand, it only enforces the length checking for copy to user. Other critical kernel functions for data transferring are not included. On the other hand, the legit length range is not restricted enough. The sensitive data can reside in the cache slot or stack frame. It's still possible to leak them even after the mitigation is enforced. According to our discussion in the previous slides, there are now no mitigation in the kernel that can perfectly neutralize the threat of elastic objects. To this end, we propose a new defense mechanism. This mechanism isolates elastic objects that we defined or that we identified into individual shadow caches. To be specific, we create an isolated shadow cache for each general cache during kernel bootup. Using shadow caches, we store elastic objects with the corresponding sizes. For example, the elastic objects originally allocated in kmalloc 96 will be assigned in kmalloc isolated 96 after the isolation mechanism is enabled. To support this isolation, we modify the kernel source code by adding one more flag at the allocation site. This flag specifies that the object to be allocated is an elastic object and should be placed in the shadow caches. Within the isolation mechanism, an adversary has little chance to leverage the vulnerability tied to other objects to manipulate the length field and the pointer field in elastic objects. Besides, the common heap spray objects and kernel objects with sensitive information like function pointers are also isolated from the elastic objects. They could not be used for heap function and spraying. I learned from Security that they have implemented more advanced isolation in their new defense named AutoSlab. AutoSlab is much more aggressive in heap object isolation. Although I don't know more details about AutoSlab, I'm pretty sure that this security improvement is very significant too. We evaluated the performance overhead of our proposed mitigation. We used 3 sets of benchmarks. The first set is micro benchmarks from LM-Bench, which test the latency and the bandwidth of common system calls and I/O operations. The second benchmark is macro benchmarks from Pharonics Test Suite 9.8, which runs 5 real-world applications. To prevent the overhead from being hidden behind sophisticated kernel execution, we specifically designed the third set benchmark to stress test the impact of our mitigation approach. This set of customized benchmarks use the system call sequences to reach elastic object allocation and corresponding data leakage intensively. Overall, we could observe that the performance overhead is negligible, with average performance drop less than 1%. We also evaluated the security improvement of our proposed mitigation approach by reusing the 31 vulnerabilities that we used to study the generality of elastic object attack. For most vulnerabilities, we cannot find elastic objects that can be used for exploitation. It is because elastic objects and the vulnerable objects are mostly different. They are isolated into 2 different caches. There is no longer a possibility to use the vulnerable objects to manipulate the length field of an elastic object. For vulnerable objects in CVE 2017-71-84 and CVE 2017-17053, there are also elastic objects allocated in shadow caches. Technically, they can be leveraged to override data in isolated caches and thus manipulate the length field of an elastic object for data disclosure. However, we argue that even this situation exists, our mitigation still raises the bar because the disclosed data is not likely to be useful for bypassing kernel mitigation. Taking the practice of circumventing KSLR using CVE 2017-13053 as an example, to use a vulnerable object to reveal a kernel-based address. In addition to leveraging the elastic object, an attacker usually has to identify a general object that encloses a function pointer. Then the attacker needs to place the object in the same isolated cache. However, due to the isolation between general object and elastic object, such a general object is no longer available for this isolated cache. In addition to the defense we proposed, there are alternative defense solutions we've ever considered. The first possible solution is to build shadow memory for each of the elastic objects allocated in the kernel. In that shadow memory, we can record the actual size of the corresponding object. When the kernel discloses data in a flexible buffer at any leaking ankle, we could check whether the amount of the data migrated to the user space is within a legit range. Since the construction of shadow memory inevitably introduces memory and performance overhead, the key challenge of this solution is to develop a lightweight method to minimize overhead in a systematic method. Another possible solution is to design a mechanism to enable the integrity check for the data in length field. We introduce a checksum field. When the kernel allocates a corresponding object and initializes its length field, we could encrypt the length value and store it in the checksum field accordingly. With this design, at the time of disclosing data in the flexible buffer to the user land, the kernel could easily retrieve and examine the checksum. The key challenge of implementing this idea is to ensure that addition of the checksum field will not influence the usability of the kernel. Some elastic data structures are designed for protocols which have specific formats. After allocating objects in these types, the kernel references the data through corresponding offsets. If introducing additional field into such objects, one has to ensure that the newly added checksum field does not incur incurrent data reference. I summarize the takeaway of the presentation as follows. First, using elastic object for leaking is a severe and general approach to bypassing protections in kernel. Second, new mitigations are needed in Linux FreeBSD and XNU to prevent elastic object attack. We evaluated our proposed mitigation and showcased that its performance overhead is negligible while security improvement is clear. Finally, it seems that elastic object attack for arbitrary writing is less general, but more study is required to confirm this claim. Thanks for listening, and thank you very much for having me here. If you want to know more about me and my other projects, or you don't have a chance to ask questions in this session, feel free to follow me on Twitter. Contact me using email and check my personal page. We've released the code on GitHub and welcome your contribution. Thank you all.